Okay, so this video will be on worksheet 13, question 2, A-star search. And why don't we begin by looking at each of these searches briefly that are mentioned in parts A, B, and C. So uniform cost search, remember, is the same as Dijkstra's, except that rather than finding the distance from the starting node to every other node, we're given an ending node that we care about, and we terminate uniform cost search as soon as we reach the end node. So recall that Dijkstra's finds the shortest distance from the start to every other node. Uniform cost search uses the same algorithm, except we terminate once we reach the end node that we care about. Greedy search, in part B, is a search based on heuristics. And so what is a heuristic? So a heuristic is a measure for each node, and it estimates the distance from that node to the goal. So for example, let's look at node D. We see that h equals 2. And that means we estimate that if we're at node D, it's going to take us a cost of 2 or a distance of 2 to get to the goal node, G. So then that means if we look at the goal node, we should have a heuristic of 0, right? Because if we're already at the goal node, then it should cost us nothing to get to the goal node. And in part C, A-star search, so this is what the question is trying to focus on here. It's a combination of the ideas of part A and part B. So the priority we use to evaluate sequences or paths in A-star search is a combination of the cumulative distance of uniform cost search and the heuristic of greedy search. And we're going to go over each of these in detail and visualizing the queue as we go along. So let's start with uniform cost search. Remember, this is essentially the same as Dijkstra's, so we're going to maintain a priority queue, and specifically it's going to be a min priority queue, which means items that have lower priorities, that have lower values have higher priorities. And so I'm going to represent each path or each sequence as the letters in the sequence as a tuple, right? So as the letters in the sequence followed by the distance it takes to get to the final place in that sequence. So for example, the first thing we're going to add to our queue is just the starting node, right? So it's going to be S, and the distance is 0 because it costs us nothing to get to the start. Remember, we're trying to get from start to goal here. Okay, so the next thing that UCS will do is remove the smallest item in the queue and replace it with all of its children. So in this case, S only has one child, SA, and the distance is 1 because it cost me a distance of 1 to get from S to A. And so at this point, I have to remove SA, right? And I'll replace it with all of SA's children, which is SAB, SAD, and SAE. So for SAB, my distance is 2, right? Because 1 here and 1 here, so that's 2. For SAD, I'm going to have 4, right? Same logic. And for SAE, I'm going to have 9. Cool. Yeah. Okay. So at this point, what is the smallest thing in our queue, right? And remember, the smaller the item, the higher the priority in a min queue. So right here, we see that SAB has the smallest value, so therefore the highest priority, and we remove it first.
And when we remove it, we add in its only child, SABC, which gives us a distance of 3, right? And then everything else remains the same in the queue.
Now we repeat this process. We see that SABC now has the lowest value and the highest priority, so we remove it. And so SABC actually has no children, right? So we can't add anything to the queue. We remove it, but we're done. So we simply remove it, and SAD4 is still there, and SAE9 is still there. Oh, and one thing, notice that I'm actually not ordering these things necessarily, right? Like I'm not enforcing that, oh, this must be before this or this must be before that. And that's because it doesn't really matter, because the only thing I care about right now is popping things off from the min queue. And from a min queue, as long as I have these priorities, right, like these second numbers in the tuples, then I know which one is the next to be popped off. So that's really the only thing I need to keep track of in this problem. Okay, now the next smallest item is SAD4, right? So we pop off SAD4 and we replace it with all the children of SAD. In this case, it's just SADG.
And that's going to give me a value of 1 plus 3 plus 2, which is 6.
Okay, so notice at this point, I actually have a sequence in my queue that includes the end node. So does that mean I'm done? Well, not necessarily, right? In this case, it does mean that I'm done because the next thing to be popped off is SADG because 6 has a higher priority than 9. However, you can imagine that, let's say I have some other thing, right? Like let's say I have SAEG in the queue as well. And for whatever reason, this is not true for this graph, but let's just say like the priority for this, or the distance, the cumulative distance for this is something smaller than 6, like let's say 4, right? Okay, so let's say that was 4. Then in this case, I would actually return SAEG as my path. So what I'm trying to get at here is that if I have two sequences, right, that both have the end node, that both include the end node, then the sequence I return is whichever one I would pop off first. And that is always going to be the one that corresponds to the lower distance. Because remember, in a min queue, we always pop off the smallest one first, right? Okay, so in this case, this does not exist. And so my answer is just SADG.
Cool. Let's go on to greedy search. Part B.
Okay, so similarly, we're going to use the exact same structure, a min queue, and we're still going to use a min queue, so we're always going to pop off the smallest element first. But the only thing we're going to change now is the heuristic, or sorry, how we calculate the priority, which in this case is based on the heuristic only. So for S, the beginning, right, our heuristic is no longer, or sorry, our priority is no longer 0. In fact, it should be 6, right, because I'm looking at the heuristic. So now my priority is only based on the heuristic. And because my starting node has a heuristic of 6, that's going to be my initial item in the queue. Okay, so now I pop off S6 and I get SA. And what should the heuristic be here? Well, it's not 6 plus 5, it's just 5. Right? We only add the heuristic of the most recent thing that we're at. So SA means that we visited A from S and we're at A. So we add in the heuristic of A, which is 5. And you might be thinking, like, why don't we add heuristics? Well, that's because remember what a heuristic is? It's defined as an estimate for each node to the goal for that node. So for example, a heuristic of 5 at A means that we estimate if we're at A, it's going to take us a distance of 5 to get to G, right? So it doesn't make sense for me to add like this 5 to this 6, right? Like this, physically it won't mean anything. So we only look at the heuristic of whatever node we're currently at. Okay, so from SA5, it's the only thing in our queue. So we pop it off and we add all the children, right? So that's going to be SAB with a heuristic of 6, right? Because B's heuristic is 6. We have SAD with a heuristic of 2. Oh, shit. Okay, SAD with a heuristic of 2. And finally, SAE with a heuristic of 1. Okay, so what's the smallest thing in our queue right now? Well, it's SAE, right? Because 1 is the smallest value I have. So now I'm going to consider that, remove it, add all its children, right? So everything else remains the same. And now I remove SAE, so I add in SAED, right, with a heuristic of 2, and also SAEG, the heuristic of 0. Okay. So now what's the smallest thing in my queue? Well, it's SAEG with 0. And remember, at the point we pop off the sequence which contains the the goal state, we're done. We can return that as our answer. So in this case, our answer is SAEG, and the heuristic at G, remember, is 0. And so if you've been following this along, like you might notice something, right? Like because we only look at the current, or like we don't add up the heuristics, right? Like we only look at the most recent heuristic. Well, what that means is we can eyeball this really easily. We can start from S, and at every step, we just take the smallest heuristic that is available to us. So for example, in this case, we'd have S and then A, and at this point, the smallest heuristic available to us, right, we can choose from E, D, or B. We can choose from 1, from 2, or from 6. And because 1 is the smallest here and it corresponds to E, we go to node E next, right? And then we do it again. So from E, we can visit either D or G, and we see that G has a smaller heuristic of 0. So we go from E to G. And so our final path is SAEG.
Cool.
Okay, finally, let's do A star search. So now we're going to combine the ideas of parts A and B. Okay, so the priority, instead of being just the cumulative distance, like in part A, or just the heuristic, like in part B, is going to be a combination of those. And what the combination is simply the sum. So let me give you an example of that, right? For the first node, the starting node, the distance is 0, right? Remember here? And the heuristic is 6, remember here, right? So we just add 0 and 6, and we get 6. Next thing is SA, right? And the distance it takes for me to get from S to A is 1, and the heuristic at A is 5. So we add 1 plus 5, and we get 6. And now SA is the only thing, so I remove it, right? And I'll get SAB, SAD, and SAE. So for SAB, I'm going to have 1 plus 1 as my distance, plus 6, which is the heuristic. And that's going to give me 8. Okay. Similarly, I'm going to do the same thing for SAD, right? And that's going to give me 1 plus 3 plus the heuristic, which is 2, which is 6 in total. Okay. And for SAE, I do the same thing, right? 1 plus 8, which is 9, plus the heuristic 1, and that gives me 10. Cool. So now at this step, right, again, we always pop off the thing with the highest priority or the smallest value. So in this case, SAD has the smallest value. So I'm going to leave everything else. And I'm going to pop SAD. And the only place I can get to from SAD is G. So my sequence is going to be SADG. And now the distance is going to be 1 plus 3 plus 2, which is 6, plus the heuristic, which is 0, right? Cool. And then this remains the same. Now at this point, what's the next thing I need to pop off? Well, it's just SADG, right? Because 6 is smaller than everything else in the queue here. And notice that SADG contains the goal state. And remember, whenever I pop off the goal state, I can return that as my answer, and I'm done. So my answer is SADG. And let's move these questions closer to their respective locations. Okay, so notice, like, why do we bother with A star search, right? Like, oh, it returned the same thing as uniform cost search. Like, what's the point of adding these heuristics and whatever, right? Well, it's because notice that in uniform cost search, we actually visited the wrong way before going the right way. And what I mean by that is, if we were just to eyeball this, right? This is a simple graph. Like, we can just see, oh, SADG is the answer. And even if you couldn't see that right away, you could sort of figure out, like, oh, G is to the right of S, so we definitely should be going this way. We definitely should be going right from S. Like, we definitely shouldn't be going SABC, right? Because C just gets you farther away from G. But uniform cost search doesn't know that, right? So uniform cost search is going to actually explore SAB, and then it's going to say, oh, SAB only has a priority of 2, right? Or sorry, only has a value of 2, so it has the highest priority. So now I'm going to pop this off and explore SABC, right? And then we realize, oh crap, SABC is not the answer at all. Like, G is not this way. In fact, SABC has no children. So my point here is that uniform cost search is what we call an uninformed search, right? We don't have anything to help us kind of point us in the right direction. So that's why we end up exploring unnecessary places like SABC. Notice that in A star, we didn't explore that, right? Like, once we got to SA, we did SAB, SAD, and SAE because we had to add all the children of A. But after that, we immediately got to the right answer of SADG. And that's because A star search is informed, and in this case, the heuristic is what we call admissible. And an admissible heuristic, you can just think of as a heuristic that will never overestimate the true distance from a node to the goal. It'll always be an underestimate.